Okay, so going to get going. So, ladies and gentlemen, for today's exercise, we're going to be reinforcing some points that we started to make last time with the comparison of agent-based modeling and compartmental modeling. And we're going to be doing so by additionally examining some mechanisms in agent-based modeling state charts that we saw at a beginning level last time. State charts describing a characterization of the states in which an agent can be present, a characterization of the rules for, the actions for transitioning between those states, and the rules that govern the firing of those actions, under what conditions someone goes from one state to the other. We're also going to look at the inclusion of networks into today's model. Networks are going to be a substantial subject of discussion within the next few weeks here. We're going to be going into an analysis of the impact of different network structures on the dynamics exhibited in the simulation, and a discussion of particular classes of networks, particularly scale-free networks, to examine the ways in which they govern the behavior of a model. So within today's modeling, we're going to be examining the impact of networks in an agent-based model on the dynamics of the model, and comparing it to what we get from a compartmental model. We are further going to use this time to reinforce some elements of analysis of these models, particularly extending the whole notion of equilibrium to a stochastic and agent-based context. Okay, so we are going to go here, and first thing we're going to do is to go to our course site. So I'd like you to go to Moodle and download the model that we built about a week ago. It's possible that some of you will already have it, but if you don't, you'll definitely want to do this. It's called SIR Model 1 on mine. And this was a model that we created to simulate the spread of infection in a population a few lectures ago. And I'd like you to download that. When you do so, it's possible it will open it up for you in this sort of fashion. What I will try to do here, if it does that, is to see if we can get it to simply download it. There may be the way to do that in Moodle, but give me a second and I'll make that the default here. I had neglected to do that, and I should have. Okay, so what we want to do is we want to make it so when you click on it, it forces a download. Okay, so you can, you should be able to refresh and do that now. So when you click on this now, it should download it to your computer, SAR Model 1, from the Moodle site, okay? Again, if you have this model on your computer already, you are welcome to use it. Okay, the next thing we're going to do is to call up AnyLogic. So I will go here and call up the version we'll be using. And our first action is going to be to open that model and save it under a new name because we're going to be comparing that model side by side with a corresponding, at some level, agent-based model. Okay, this is going to be a compartmental model reference, and we're going to compare, much as we did last time, an agent-based model to this point of reference. Okay, we're going to compare and contrast the behavior of these two different types of models as they characterize a single situation. Okay, so while this is coming up, I'd like to ask you to remind me, when we saw the results last time, comparing the simulation model made with an agent-based approach versus an SD approach. How did they compare? Anyone? How did they compare last time? Yeah, they're almost exactly the same. Why were they not exactly the same? Why were they not precisely the same? What was different between them? Do you remember? There was actually a slight difference between them. Both exhibited basic features of a first order delay, but what was the difference? It turns out in the agent-based model, there were some fluctuations. There were some fluctuations over time. What did these fluctuations correspond to? Why did we see fluctuations? It didn't quite line up with the line from the system dynamics model. Why not?
Because contact might not be a constant.
Yeah, so that's good. It turns out that model didn't have contact, but it did have recovery. So it had transitions. And the point was that within that model, the transitions were stochastic. What do I mean by stochastic? Anyone? Yeah, it's random over time. So it exhibits randomness at a given point in time. And as one goes over time, for every little bit of time, it's got more randomness being applied. So the exact timing of an agent leaving that stock was drawn from a distribution. In fact, it was drawn from an exponential distribution, how long they spent in that stock. In system dynamics model, it assumed that for a small bit of time VT, exactly X, the number of people in that stock, times alpha, the hazard rate of leaving that stock, times dt, number of people would flow across in that little time dt. So the flow was alpha times x, had a formula of alpha times x out of the stock. And that is an approximation to an underlying stochastic process, which was in fact captured within the agent-based model, okay? So here we're going to explore those stochastics a little bit more. So I'd like you, after any logic is up, to close any of the any models you already had open, and I'd like you to open up this model that was downloaded, okay, or the model that the SIR model 1. And we're going to build the top of this model because we don't have time to completely reconstruct this model and build an agent-based model that compares to it. And I'd rather start with a model that that's a common point of reference. We're going to actually add to it slightly, and then we're going to veer off into the agent-based modeling. So I'd like you to take this model, and I'd like you to save it as, and this will be called SIRS model ABM and SD. In other words, it's going to be a model of susceptible, infected, recovered, and then susceptible. People will lose immunity for both ABM and system dynamics simultaneously. So we're going to save that away. Okay? And by saving it away, we're going to be able to modify it without wrecking the original. Okay, so I'd like to take a look at this model, and I'd like you to remind me, what was the result of this model? So here we have susceptible, infected, and recovered people, and this captured sort of the classic thing we've been talking about a long time, where the force of infection is some transmission probability beta times, or I'll do it in the same order I normally do, contacts per month C, times some prevalence of infection, I over N, the fraction of people that are infected, times some transmission probability beta, that's the force of infection. And the incidence at a given time is just the force of infection times the susceptible. Force of infection is the chance per unit time that a susceptible will get infected. Okay? So what did this model yield? When we ran this, we had people starting, 1,000 people roughly starting susceptible, and one person starting infective. What did we see in this over time? Anyone remember? What happened? What pattern came out of this?
If I remember correctly, it was susceptible was kind of decreasing. The curve way.
Okay.
Effective was increasing.
Yep.
And recovered was just
Good.
decreasing.
Good. That's exactly right. And recovered sort of went up, and it went up to some cumulative level. Was everyone in the population eventually infected? No. The fraction of people in the population that were susceptible eventually went to such a low level that infection couldn't spread. And it turns out that that's not zero. So there's some residual susceptibles, as shown in green here. There's some people at the end who remain susceptible, but it's such a low level that infection is not sustainable, and it does that. Do you remember this? Do you remember this? Okay, hope so. Hope so. Okay, so ladies and gentlemen, here's our little reference model. We are going to extend this reference model. We're going to do it in a way that will be amenable to analytic solution, which is something you will explore, as well as at home, as well as to solution here using computationally. Okay, so what I'd like to do is I would like to take this nice little model, and I would like to add in a flow that represents waning of immunity. So the fact that we're going to posit now that people within this model don't stay permanently recovered, rather they lose their immunity after some period of time. They become susceptible again. So how would I do that in this model? I'd add a flow from where to where? Whence to whither? Yeah, recovered to susceptible. So let's go add that in. We're going to add a flow. We're going to add a flow in, and this is going to make the whole thing more interesting. The infection is going to stay circulating within the population, okay? So here we go. We're going to go add in a flow from recovered here, and that flow is going to flow over to susceptible. And to make it, avoid it being horrible in its appearance, even to me, I'm going to double click here to bend it to my will, okay? Here we go, and I'm going to do another bend of it here. This isn't nice, but this isn't an art class. So we'll put it something like this, okay? There we go. And really, if I had my druthers, this would, I probably should have done it more like this. Double click here to eliminate that. And then we've got something like this. And I'll prettify it a little bit more by, okay. My attempts at prettification have failed. We'll just live with this. Okay, so this flow is going to be called waning of immunity. Waning of immunity, okay? And we are going to add a parameter called mean duration of immunity, okay? Mean immunity duration, And that will be a default value of 270.0. And I'm going to tell you that waning of immunity flow will just be a first order delay, leaving recovered and going over to a susceptible. So what's the formula for waning of immunity for this flow, given that it's a first order delay dependent on waning of immunity parameter, our mean immunity duration parameter? What's the formula for waning of immunity? I'll give you a hint. It depends on recovered, and it depends on this mean waning of immunity. But what's the formula? What does it have to be dimensionally correct? Yeah, it's people per time. Good. So what's the actual formula? Yeah, recovered divided by mean immunity duration. Okay? Ladies and gentlemen, 270 days, right? We know this model has time units of days, because if we go click in the model up here, oh, it's months. Oh my gosh, it's months. Well, mumble. Okay, fine. I will make it months instead. So 270 here. Whoa, sorry. 270 divided by 30 here, right? So by 30 will be 9 months. So change mean and immunity duration, it needs to be measured in months because the time unit of the model is months. So I'm going to make this 9 months, okay? 9.0 months. I said 270, but I need to adjust for the fact it's month. I was thinking if it was in days, okay? Although, wait a minute, mean time to recover is actually very, yeah, so this is 10 months. Sorry, folks, change this back to 270 because looks like I was scaling everything to be months. Okay, fine, 270. Great. Okay, so how is this going to change? How is this one going to change the dynamics of this underlying model? Anyone? How will this change the dynamics? Sorry? Yeah, good. It won't reach equilibrium. So the system, or it won't reach the same equilibrium where the infection dies out. Will the infection die out here? Is the infection going to die out now? Okay. It's conceivable that it could if it's not sustainable from the very get-go, like if the transmission probability is too low or the number of contacts from the very start, so that even with a person surrounded by all susceptible, if they infect fewer than how many people will it die out? Fewer than 1, then it will die out. So that's a possibility still. If the infection takes off initially, will it ever die out? The answer is no. What's going to keep on happening? What is it that dictates whether an infection dies out or not? Yeah, you run out of susceptibles, just like a fire runs out of fuel. Is it going to run out of susceptibles here? No, because people are going to be coming back. They're going to be coming back from the recovered state. So let's go run this thing, and let's go see what happens. Okay? So we're going to go run this. Here we go. And what do you think we'll qualitatively see? What will happen the first little bit? What's going to happen in the first little bit of the model run, do you think? What's it going to look like? Very good. It'll look quite similar. And then what? What's going on here? What's different from before? How is this different from what we saw just 3 minutes ago? What? Yeah, okay. So what's going up at the end? Susceptible. Okay, let's give us a little bit more time if we could. Let's go change this graph to give us not just a window of the first 100 months, but the first let's say 1,000 months, okay? 1,000 months. So I'm going to go here. I'm selecting this time plot, and I'm going to go over to here, and we will go down. We'll say display up to 1,000 latest samples, and the time window will be 1,000 in length. So we're telling it, hey, display over a time of 1,000 and keep all the data till then, so it doesn't sort of start to eliminate earlier points. Okay, now I'd like to run it. What do you think we'll see now? If we extend the time, what are we going to see that's different now? What's going to be different? Where will that go? That thing that was edging up, the susceptible edging up at the end, what will that lead to? Oop. Oh gosh, I didn't tell this. Yeah, it'll lead to a loop. I like it. So I got to also set the simulation to run to time 1,000 instead of 100. Sorry, folks. Not just the plot, but also set the stop time to be 1,000 for the simulation. So it'll stop at specified time. This is for the simulation itself. Okay, so let's go run it. Here we go. We're running it, and we will. Good. So it's going to loop, I heard, and then that's to a degree that's true. Here we go. Gosh, what's happened there? Well, it's kind of a loop. It's a loop in what sense? Well, we have multiple outbreaks, but the outbreaks are damped. Outbreaks are damped. They're getting towards an equilibrium. A what sort of equilibrium? And begins with an E. Endemic equilibrium. What is the case roughly at this point where the red goes to, where the infectives is stable? What has to be the case there? Inflow equals outflow to infectives. Good. So incidence equals the rate of incidence is rate of recovery. Alternatively, each infective infects how many people before recovering on average? Roughly 1, right? And that's where this fraction of susceptibles is going to. So we get these sort of oscillations as it comes down to this equilibrium. And you may recall back when we were discussing first order delay, so we put in place a delay with a first order delay. What would happen? We got oscillations. We got oscillations that could overshoot and then undershoot, and overshoot and undershoot. First order delay, if it's delayed, it's like, you know, you're not seeing, you're not judging properly where your car is on the ice, and so it fishtails because you overcompensate and it goes back and forth, just like that here. But this is what we see in the aggregate model. Now, ladies and gentlemen, we take a sharp detour. We're going agent-based now, and we're going to compare our results to this. But first, we got to build up an agent-based model with contagion in it. And it is to that task that we will now press ourselves, okay? So let's get down to work. Okay, so ladies and gentlemen, I would like you to go to this model, and I would like you to add a agent class into it. That is a characterization of agents, of agenthood, of agentness. That's what this class will represent. So I did new agent type for the model, and the agent is going to be called person, capital P. We're representing what it means to be a person in this model, what it means to have personhood, to have personness. Okay, so here's our person. That's our class, and let's give that person a face upon the world, if we could. Okay, so we're going to go down to the palette. And we are going to add in a person. And I know the jokesters amongst you will be adding other things. So we just added in a person here. Person, we put it right on that crosshair because we want their visual position to be same as their logical position. So they're placed visually right on top of the place where they are logically. It'll help their reasoning. Great. Now we're going to rehearse another thing we did last time. We are going to add a population of people. How do I do that? How do I add a population of people here? I went and added a person class. I defined what personhood means, and I added a picture associated with that person. How am I going to add a population of people? Whither do I go? I go to Maine, indeed, and it is in Maine that population will live. So I go to Maine, and then what do I need to drag into Maine? From where? Whence does it come? From person, ladies and gentlemen. From person. We're going to drag in from that person class and drag into Maine, okay? So you drag this in like that, and we're going to call it population. At first, it just naively calls it person, but we know we wish to turn this into a population. So we're going to call it a population, but does it actually make it so? Not yet. We need to make it a population of agents. So whilst you are holding this, I'm going to make it a population of agents of size 1,000. Why 1,000? Where does that number come from? Whence does that come? Why 1,000? because I want it to be comparable. The population of the system dynamics model is 1,000, so I want this to be 1,000, just to be comparable. Now, had we more time, I would make that based on a parameter, and we may come back to that. But for now, we're going to leave that. Okay? Okay, ladies and gentlemen. So we've changed that to 1,000, and we said it's a population of agents. We are now going to place these agents at random positions in the X and Y directions. How do we do that? Anyone remember from last time? Yeah, go to initial location and specify at the specified point, and we're going to draw it using a uniform distribution between 0 and, okay, now I can't stand it anymore. I cannot, I can't stand it. I can't hard code these things in good conscience in front of a group full of students. I'm corrupting the youth. I can't stand this. I refuse to consider. So I'm going to do it between 0 and space width, okay? So it's between 0 and the width of the space. And so if I change the width of the space, it will accommodate accordingly. None of these hard-coded nonsense for me. After I'm at, you know, how can a software engineer have dignity putting magic numbers everywhere? I mean, have you no sense of dignity, no sense of shame to put in these magic numbers? We gotta keep ourselves honest. A good, healthy sense of shame can be a good thing. So we're gonna do space width and space height. Magic numbers lie beneath our dignity, ladies and gentlemen. Just sprinkle them around gratuitously. In times where there's a conscious trade-off, okay, but we won't give into it reflexively. So here we're drawing their X location between 0 and the space, the width of the space, and their Y location between 0 and the space height. Ladies and gentlemen, autocomplete is your friend. Control space on PCs. Think it's option space on Macs. It will fill out those names. This is Eclipse behind the scenes, and for those familiar with Eclipse, you can leverage the features of Eclipse in that regard. Okay, so now let's build our model. Make sure it's a happy camper. If we were to run this model now, what would we see? What would we see in front of us? What specter will lie before us?
Just be the population.
Good. Good. Okay, so there'll be a population of people scattered around the space. Some of them inconveniently placed by the stock and flow and the graph and so on. But they're sitting there within the space with not much happening there. Okay, fair enough. We're going to now go and we are going to do something that we haven't done yet. We are going to put these people into a network. In other words, we're going to establish connections between these individuals. And these connections will be placed between individuals according to certain criteria. And we're going to actually see about 5 or 6 types of networks within this class. The network here that we're going to impose is particularly easy, and it's particularly easy to understand and to describe. The network will be such that any 2 pair of people will be connected if and only if they lie within a certain distance of one another. Okay? And the way we're going to do this is something that you'll need to follow carefully. So each agent in any logic maintains the networks, the default network actually, for agents that lie within it. Okay? That lie within that agent. So we're going to go to main because the population here lies within main. And we're going to scroll down to space and networks. Okay? So we're going up to main. Scroll down to space and network over here in the properties. And we're going to find the network type. And we're going to change that from user-defined to be a distance-based network. Okay? And we're going to have a connection range, ladies and gentlemen, of 50 will be fine. We'll do 50, okay? Connection range of 50. Okay, are we okay with that? Okay, now, there's one other thing that I want you to do though. So we're going to impose these networks, and we need to show these networks, okay? We're going to make them visible. And it turns out if we ran this now, there would be a network, but it wouldn't be obvious because the people aren't obviously connected to one another. They would be, and I could show that in other ways, such as by changing their scale and so on. But I'd prefer it if we could just make the network visible. So we're going to go to person here. And by going to person, mind you very carefully, yes?
I was just wondering, what are the units for the
space? Okay.
yeah, for the network?
Yeah, okay. So good question. So I'm going to answer that question in two ways. The first is that if you were to go to main, or indeed person here, and you were to scroll up above, you can see that there's a scale here, which indicates the correspondence between a visual scale, which is actually what's being referred to in that distance for the network, is the visual scale, where 10 pixels constitute one of these squares. And it indicates the correspondence between that and physical scales, like meters, or it could be kilometers, etc. And naturally, for different models, we want very different scales. If it's a GIS model of a geographical area, we might have each square here corresponding to 10 pixels be 1 kilometer or something. But here, what we have is each of these squares is 10 pixels. And when I said 50, it's actually referring to 50 pixels here. So it's each of the width or height of one of these big squares is what I said. Connect people if they lie within that area, okay, of each other. But if you want to translate it into physical scales, which we will come to talk about the speed of movement on roads or paths or what have you, or within a hospital, you would actually want to be thinking about the physical correspondence here. And you can change that as well, any logic. Okay, so good question. But here, I'm going to person, ladies and gentlemen, and I'm going to connections, okay? I'm going to connections here. And I'd like you to go into connections and go down to the animation area. And I'd like you to do a checkbox on this box, this checkbox. I'd like to put a check, a tick mark in this box under animation. It says draw line connecting agents. Okay? Okay? So what this is going to do is, if there is a network, they're going to be shown visually as connecting, okay? And if there's a network in this connections area. Okay, I'd like you to run this model now. Any questions on what I just did? I know I went through a couple steps, briefly rehearsing. I went to main. I went down to the network space and networks area. I set it to be a distance-based network with a connection range of 50. I then went to the person, and I went to their connections, which you have to scroll up to see. In other words, look up above them to see the connections. And I went down to the animation area, and I ticked the checkbox, which said connect to neighboring agents. Okay, so I'm running this model now, and lo and behold, people are going to be connected up in a network. And you can see that network lying behind them. Do you see that there? Do you see them there, network? Okay. Okay. So now we have people connected to each other if they lie within a certain distance of each other. They look a little bit dense for me, so I'm going to actually scale it down in main. We're going to change the range down to 30 because to make it a little less dense for the purposes of our demonstration. So if you go to main, go down to space and network, you can change the connection range to 30. And by running that model, you'll see that we've thinned the network. So before, any two people, A and B, who lay within 50 units of each other would be shown as having a connection between each other, would be connected in the network. Now they have to lie within 30. So we've made it a tighter constraint, a tighter set of criteria. And that's something which is going to require sort of fewer connections in total. Okay, so there we are. People are going to be connected a little bit more thinly now. Do you see that? So any two people here, A and B, are connected if and only if they lie within 30 units of pixels here of each other. So we have people locally connected. They're connected with other people nearby them. Yeah? Okay, ladies and gentlemen. Next. So that's all well and good. We put them in networks. Next, we're going to go have some dynamics for these people. We're going to implement a change in infection status over time associated with these people that mirrors that lies within the system dynamics model. Here's our system dynamics model, lies behind here. And we are going to have a corresponding structure in an agent-based model. And we're going to do so using a construct that we saw last time called a state chart. Okay, so we're going to go to the palette. We're going to go down to the state chart area, and we're going to drag in a state chart entry point. And this one's going to be called infection state chart. Next. So where does the state chart live? In person or main? In person, because we're describing the dynamics of a person. We're describing personhood now includes a sort of theory of how people change infection status. So I'm going to person. I put in this infection state chart, and the different states that are possible under the infection state chart are, what do you think the first is going to be? Susceptible, good. Next, what do you think the next is going to be? Infective, good. Infective, and final one? Yeah, recovered. Okay, excellent. Recovered. Good. And now we're going to put transitions between them. So the states characterized collectively, they're collectively exhaustive, mutually exclusive. In other words, you're running with respect to this particular state chart, mark my words, with respect to this particular state chart, you're in exactly one state at a time. And only one state, right? And we're going to put in transitions which specify the actions that change those states, and secondly, the rules under which those actions play out. And we're going to place them with the rules here. So we're going to put in a transition between susceptible and infective, and we're going to put in a transition between infective and recovered. And what transition is now missing? Yeah, recovered back to susceptible. Okay, so let's put that in. Now, just as in the system dynamics model, this lacks, this wouldn't end up in the Metropolitan Museum of Art. So I'm gonna bend this around so it's at least less heinous in its appearance. Okay, there we go. Okay, now I have deliberately, so what I've specified here are the actions, things that change the state. Next, I'm going to be thinking about the rules. But before that, we're going to have a little diversion to make it obvious that they're changing state. And I'm going to use this to teach some principles of the different sorts of transitions. We're going to make them very visible. We're going to make these transitions highly visible graphically, so we can see the impact of making different choices when it comes to the rules that govern those transitions. Okay, so here we go. Ladies and gentlemen, we are going to place into this person a variable, and the variable is going to be called color, spelled according to the Queen's English. Okay, C-O-L-O-U-R. Okay. This is a variable. This is a Java variable for for whom that lends comfort. The type of it is going to be listed here in this box as other, and we're going to put the type here. This is of type, can be a reference to some instance of the color class, which is defined according to the dictates of the American Imperial, forsaking the Queen's English and using the American spelling. So with a capital COLOR, because it's a class. It's an instance of this class. It's one of a set of colors. And we'll make its initial color, ladies and gentlemen, black. Okay? Initially going to be black. Okay, now, next, we are going to set it so that depending on what state they're in, that color will change accordingly. Is that okay? Does anyone need me to show something I've done? Is anyone trying to catch up and you're just puzzled by a step I've taken? You want me to show something? Anyone? Happy to show any part of this model. I'm happy to upload it to Moodle if that will be useful for anyone, if you're feeling so lost. Yeah?
Your population, your initial location, can you show that?
Sure. The population, great question, because I'm going pretty quick here. We're on a forced march. Okay, the population here is, here we go, and the initial location, I drew it uniformly between, for X, between 0 and the value returned by this call to space width, and similarly Y between 0 and this call to space height. Okay? Okay. So I'll go and have a look. Okay. So oh yeah, it's 0.0, not 0.0. Yeah. The reason I put that in is there's a long story here, but fundamentally, it is valuable if people, when they refer to a double, they write it as a double, because probably a certain fraction of this room has been burnt by that bug in Java where you say like 3 divided by 4, and you mean it to be 0.75, and it comes back as what? 0, because it's an integer division. Yeah, I feel your pain. Been there, done that. Sometimes I express it in stronger language. And so I often will tend to write like 0.0 when I just mean it at 0 as a double precision value to avoid those stupid things. Is that helpful? Clear it up? Yeah. Okay. Other question? Yeah. Sorry, no connections?
Yeah.
They're not connected.
Yeah. Well,
oh, yeah, you have to choose network type distance based. So good question. Here. Mumble. That's really interesting. Okay, so it's not allowing you to choose the network type. Mumble. Okay, close the model, reopen it and check. Okay. So ladies and gentlemen, one of the members of the class had an issue where in main here, if you go up to main, they went down to in main the, are you in main? Are you looking at the properties, Alex, to main? And you go down to space and network. The network type should allow you to pick distance based, and this connection range won't appear unless you choose distance based. Okay. And at that point, it will allow you to pick it. Anyone else? So this should be 30.0 by my token. Okay. So anyone else? Okay. Anyone else need any pointers on this model? Yeah. It should be distance based here. Because we're connecting people if they lie within a certain distance of one another. So we want. Sorry. Yes. This if two people, A and B, are connected if and only if they lie within the specified connection range of each other.
Oh, so the connection range is the distance.
It's the distance, yes. That's the distance. The distance is used as the criteria to connect them. If A and B lie more than 30 pixels apart, now again, I did pixels here, and pixels are related to meters using the thing we saw earlier. And so this says if they lie within 30 units of each other, each of these little squares is 10. It's really small squares is 10. They lie within 30 of each other, they'll be connected. Otherwise, they will not be. Okay? That was picking distance based from that. Okay? And again, I'm operating here on main, the space and network properties of main. Okay? Okay. Okay, ladies and gentlemen. Anyone else? Question? Okay. Okay, so let's move on because we still have some miles to cover. We've made good progress, but we've got to do a number of additional things. Okay, so ladies and gentlemen, in susceptible, back in person, we're going to go to susceptible. And in susceptible, if they enter the state, we're going to set their color to be green. So I could say this dot color, and of course it's with a OUR, equals, we'll say lime. It's lime green, ladies and gentlemen. Okay. Next, notice the semicolon because that's a command. We're saying do it. So there's a semicolon. If we go to infective, it's a statement in Java, as we say. We go to infective, this dot color equals red. And similarly for recovered, this dot color equals gray. I always forget whether it's an E or A. I think it's mumble. It's a with an A. Okay. Okay. Gray with an A. Okay. Good. Ladies and gentlemen, now we've defined the colors here that we want this person to appear. And I like to color it visually accordingly. So I'll make this one gray. Boom. And then I'll make this one, this has no impact changing these colors on the running, but I'll just change them accordingly so you can see what color it is. Okay, there we go. So here we're changing the variable to these different colors. When I come into the state, the variable will be set to red. When I come into the state, the variable will be set to gray. Now we have to connect this to what? To the little picture of the man. Now, this is slightly annoying, and the easiest way to do it is to go over to person, go to presentation, go to person, go to shape body, and set it to make the fill color. You got to go here and you got to change it from this to dynamic value and set it to be this dot color. It's declarative, ladies and gentlemen. You just say, make this person's shape have this color, this fill color. This color is referring to the variable. So when we went through each state of the state chart, we had set this variable to the appropriate color to use, corresponding to the state in which they're located. And now for this little man image, we're telling it, I selected the little man and the shape body within the man's image, and I went down to appearance. I set the fill color. You have to change it to this little recalc icon. You see that? You see that recalc icon? You got to change it to be this dot color. Okay? Okay, now, what should we see if we run this model now? What do you think we'll see? Good call, man. So we will see flashing colors. But are they flashing like a Christmas tree? Well, okay, it's sort of. I mean, I guess there could be a tree like this. Are they pulsing differently, or what's going on, ladies and gentlemen? They're just on a timed interval. It's a fixed time, ladies and gentlemen, between states. They're all proceeding in heinous sort of synchrony. from this state to infective, all together in lockstep. Then from infective to recovered in lockstep, boom. And then from recovered back to susceptible, okay? They're all changing in synchrony. Why is that? Because if you look at the transitions we used, you look at the transitions, ladies and gentlemen, these are what are called timeout transitions. These are transitions where we wish to specify the exact time that someone takes. Now, it turns out this is a very flexible way of doing it. I want to contrast this with what we did last time. What did we put in place here last time? For that first model we built with HBase, what was this that we used? We used a rate transition, which was a hazard rate, some fixed hazard rate, okay? And that's something we can specify. In fact, it's basically the same mathematics as we deal when you're leaving a stock in system dynamics. So I used that because it was a point of reference you should be familiar with. Certain chance per unit time of leaving the state. Just as in system dynamics, you had a certain chance per unit time of leaving the stock. But here we're specifying how long they're in that state. And here we're specifying it as a simple number. We could draw this from a probability distribution. What sort of probability distribution would correspond to a rate transition? Would have to be the exact analog of a rate transition. If we drew this from what sort of probability distribution, what distribution would that be? Let me put it another way. That if you have a rate, their length of time in that state is distributed according to what distribution? And exponential, it turns out. Okay, it's exponentially distributed, not a normal distribution, because it can't be negative. Normal distributions have tails into the negative region. But it's an exponential distribution. Okay, so you're more likely early on than later because you can only leave if you're still there, and you're more likely to be there early on. But you have the same chance per unit time of leaving given if you're there. So, ladies and gentlemen, we could draw this from an exponential distribution with, let's say, value 1.0 as its parameter, as its lambda. And that would be just as if we had a rate of 1.0 and leaving. But we could also draw this from other distributions. We could draw it from an arbitrary custom distribution. Right now, though, we're going to leave some of these as distributions, okay? So, ladies and gentlemen, what we are going to do here is we are going to set each of these to be according. And this one here, this transition here, I'm actually going to set, I'm going to call it waning of immunity. I'd like to have the name up here, so I have to do show name, and I'm going to put it over here. Waning of immunity, I'm actually going to set it to a distribution to a fixed number. And what would that number be? It will be given by a parameter in main called mean duration of mean immunity duration. Do you remember that parameter? We created that. Do you remember that? Remember or not? Okay. Yes, indeed. And now for infective to recovered, ladies and gentlemen, I'm going to set this to be a corresponding value, again, from this early one, mean time to recover. And I'm going to set this right now to be given by, so this will be called recovery. I'll show the name. And I'm going to set it to be based on a timeout for simplicity of main dot mean time mean time to recover. Okay, great. And then we're going to go to the heart of the issue, which is going to be this transition from susceptible to infected. We're going to come back to these and talk about their implications, about assuming a timeout compared to a rate. We're going to do that. But first, I want to get to the heart of the matter, rather than distracting us with some nice stuff. Okay. So, ladies and gentlemen, from susceptible to infective, should this be a rate transition? Should we make it a timeout? What do we need to do with this transition to make it, in some sense, comparable to the one we already created? What should we do? Make it a what? Okay, a rate. What would the rate be? By the force of infection. Did I hear that? Yes, force of infection. We could do that. But, ladies and gentlemen, that would be depending on the calculations in the system dynamics model. We actually want this agent-based model to be running entirely on its own dynamics. But we could do that. We could have a rate transition where the chance of getting infected is given by the fraction of people around us who are infected. But it turns out that's not the agent-based way to characterize it. I'm not criticizing that. It's a great idea. But here we want this to be done in a way that takes advantage of the agent-based paradigm. So we're going to set this transition to be a different sort of transition. And in fact, we're going to see how that's used in our networks in just a moment. This transition, which we will call infection, I'm going to show the name. This transition will be what's called a message transition. This can be a message sent asynchronously from one agent to another. Okay? So agents are going to send a message, and the other message, from one message to another, that you're exposed to infection. The other agent will get infected. So if this agent is exposed to infection, they will go from susceptible to infected, is the idea here. Okay? Now, turns out we're going to need to modify this, but I want to get to the heart of it, and then I want to clean it up a little bit and make it more conceptually consistent. Okay? So right now, if they get exposed, they'll be infected. Okay? Now, if we were to run this model, do you think people would start to get infected? What's missing? Yeah, patient zero. There's got to be some patient that starts the whole process off. Some patient that kicks off this whole spread. I mean, after all, each susceptible is waiting to be exposed, and then they'll get infected. But who's going to expose them if everyone starts susceptible? Because right now, everyone is starting in this state. And even if we were to start one person infected, would that impact the others? Not unless they did what? Sorry? Yeah. So they have to infect other people. And right now, they're in the infective state. They're just in the state. They're red. And then they become gray. And they're not infecting anyone. They're not interacting with anyone. What do they need to do to infect someone? They need to send a message to them. So we're going to put that in. And then we'll get to patient zero. Okay? Here we go, ladies and gentlemen. So for infective here, we're most of the way done now. For infective, we are going to put in here a link from infective back to itself. And this is going to be called the contact transition. Contact, okay? And what I'm going to do is I am going to say for each of these contacts, they're going to occur at a certain rate. What do you think the rate of contacts will be? The rate of contacts from one person to another. Where have we seen that before? A rate of contacts a number of contacts per day. Where have we seen that? In this very model. Yeah, contacts per month. Contacts per month. So we had it up here in the model, right? Contacts per month. So let's go use that, ladies and gentlemen, as the rate of contacts here, okay? Infection, sorry, it's this one here. The rate of contacts will be given by main dot contacts per month. Okay? Great. So if this person is in the state, this is going to be firing. Notice it goes from the state to the state. I mean, they're not leaving the state because it's inside the state. They're not actually leaving it and coming back in. They're just, whilst in the state, they're doing this. And what do they need to do? For each of those contacts with somebody, they need to do what? Contact them. How do they do that? By, I heard it earlier, sending a message. So for the action, you do this dot send to random connected. Send to random connected. Remember, autocomplete is your friend. Notice it's giving me all the information about it. Sends a message to a randomly chosen connected agent. Okay? And the message is going to be exposed, okay, to the bug. Okay? So now we have them sending a message to somebody. This model is not yet totally comparable to the other model, but we're gonna modify it in just a few minutes, but I want to get to the heart of it. The first thing we have to do is set this up so whilst in this state, you're sending a message to your connected agents. You get that? Yeah.
I didn't really get the link to itself.
Right. So you can think of this as while you're in this state, there's this process operating that periodically at a certain rate, this happens while you're in the state. And this is just the way of denoting it. It's like sort of saying, okay, so the process entirely within the state that goes on. Some of these processes bring you to other states, these transition processes, but this is a process that leaves you within the state, but occurs at a certain rate, as given here by contacts per month. And when it occurs, you undertake this action. I don't know if that's helpful.
Yeah. Why would we do it as like a line between infected and susceptible, like infected sending message to susceptible?
Oh, well, it's a good question. It's partly because, a very good question. It's partly because we don't know who's going to receive this message. The person that receives this message may be also already in a recovered state, or they could be an infected, or they could be susceptible. We can't dictate that. We're just sending it to one of our connections who are sending a message. And whether they're susceptible, infected, or recovered is not yet clear. If they're recovered or infected already, it's not going to make any difference to them. And indeed, that's what limits the spread of infection. It's the fact that sometimes a person who gets it can't be infected.
Okay.
Does that
help
a bit? Okay. Okay. Any other questions with that? Let's add patient 0. Okay? Ladies and gentlemen, for patient 0, we're going to go to main and we're going to introduce a new construct here. This is like a greatest hits of ABM-based model. We're going to drag into main something called initial infection. It's an event. From whence does that event come? It comes from the palette, the agent palette, event. So I drag an event. The job of an event in life is to schedule one or more events over time. You can define a whole schedule of events. In this case, we just want it to be a single event. It goes off at time what? 0. And it undertakes an action. And the action that it undertakes, so where did I go? I went to the palette, the agent palette in main, and I dragged in an event. This is all in main. I dragged in an initial infection event. In the initial infection event, I didn't change any of this because it's a one-time event. It's a timeout that occurs after 0 time. And the action is this dot deliver to random agent inside, and we're going to send the message exposed to a random agent inside this. Okay. Are we okay with that? So what we just set it to do is when the model starts at time 0, it will do what? So a random agent, which will have the effect of doing what? Given the state chart that we see here, what will that have the effect of doing? What will that agent, when they receive the message, what state are they in right now? Do we know? Everyone starts susceptible. So when they get that message, what will happen? They'll go to infected. So that will have the effect of infecting the very first agent. Does that make sense? Okay, so let's run this model. Let's run the model. Here we go. What do you think is going to happen now? Oh, what happens is it bombed out. Okay, so let's go see my problems. Okay, here we are. Contacts per month cannot be resolved. Okay, yeah. So I probably didn't say main.contacts per month or something. No, I did. Oh, right? Per months? Oh my gosh. Oh my gosh. Okay, that's horrible. Okay, I apologize. Okay, that's horrible. Thank you. Autocomplete is my friend too. Okay, here we go. Okay, ladies and gentlemen, what do we see happening here? Okay, what happened? Good. And notice that there's been a second outbreak here in the model. Is there a second outbreak starting here in the second outbreak in the system dynamics model? Is there a second outbreak in the agent-based model? Why not? Ran out of susceptibles. In the system dynamics model, you can have the infection persist even if there's only one person remaining susceptible. How if there's half a person remaining in the system dynamics model? So it's the infections that remains infected. Does the infection stay? Could it spread from half a person? How about from 0.01 person? 0.001 person in the system dynamics model? Yeah, it doesn't matter how few the number of susceptibles are. If there become a large enough number of susceptibles again, sorry, the number of infectives, how few there are, no matter how few infectives there are, as long as it's not zero, if there's enough susceptibles around, the infection will start to grow. And it will grow up to one person and two people and four and so on. So ladies and gentlemen, here within the agent-based model, we see a difference from quantization. The infection died out totally because there was no one person who had it anymore. In the system dynamics model, it stayed resident in a very small number of people and researched. Okay, let's explore this some more, though. Let's explore this some more. Let me ask this. If I ran that model with different random number seeds, 100 times, 1,000 times, 100,000, 1,000,000 times, is it possible that for some of those I will see a resurgent infection? Turns out not now, because right now recovery is dictated by an exact amount of time. So no agent, no matter how unlucky, stays infected for longer than the recovery time. No agent, no matter how unfortunate or how fortunate, stays recovered for longer than the waning of immunity time. These are fixed rates, ladies and gentlemen. These are fixed rates, okay? Now, we can go and we can modify this model further, and we're going to do that over the next 10 minutes here to examine some of the impacts here of changing some of these assumptions. So how would I make this model closer in spirit to the system dynamics model, ladies and gentlemen? How would I make it closer in spirit? So if I want a recovery to be a probabilistic process characterized by the same basic dynamics, same basic mathematics as in the system dynamics model, what sort of thing would this be? A what transition? Rate transition. Good. Rate transition. It's memoryless. Doesn't matter how long I'm there. I have the same kick of the can for the next little bit to recover. Okay. And what is the rate going to be? Anyone? Well, what was the timeout? How long was I spending there on average? It was mean time to recover. So what's the rate? Ladies and gentlemen, if I have a rate and it's leaving a memoryless, fine, call it a stop, call it a state, and the mean time I spend in the state is mu, what's the chance per unit time of leaving that state? Remember, it's 1 over mu. Now, so it's going to be 1.0 divided by mean time to recover, main dot mean time to recover. That's what it is. Okay. No matter how long they spend effective, they have that same kick of the can, same chance per unit time of recovery. Next, for waning of immunity, I want to apply the same basic principle. I'm going to change it from a timeout to a rate, where the rate is 1 divided by mean immunity duration. Okay, now these individuals can spend a shorter time or longer time infected, a shorter time or longer time susceptible. Okay? Great. Ladies and gentlemen, if I do that, if I put that into place, there's actually one thing that's important that's missing here, in which case, where this model is not comparable to the system dynamics model. Does anyone recognize it? What parameter are we not yet mentioning here? What parameter is not yet considered from the system dynamics model? It's not yet considered here.
Probability.
Yes, the probability of getting infected given exposure. Where would that go here? Where would that probability go? Yeah, it would go in the message transition. And basically you would say, if you're exposed to this message, you have a certain probability of getting infected. So I'm going to put a branch in here that's going to reflect a probabilistic transition. With a certain probability, I will get infected. Otherwise, I will stay susceptible. That's what that means, okay? With a certain probability, if I get a message, certain probability, I'm going to go on to infective. Otherwise, I'll stay susceptible. And so by default, you notice that it colors it in 2 colors. The red dot indicates the default. So I have to set 1 default. The default here will be staying susceptible. Under a certain condition, I will move. And I'm going to actually rename this one to, instead of being infection, I'm going to call it exposure, because I'm exposed to the bug. I might not get infected by it. And this one I'm going to call infection. Okay, this lower one. The upper one is going to be exposure. Here I'm exposed, here I'm infected. And I'm infected with a certain probability as given by what? What's the probability? Well, I'm going to leave. I'm going to flip a coin. Do I leave or not? And I'm going to flip the coin with a probability given by main dot, what was it called? Transmission probability. So here I flip a coin. That's what random true does. It flips the coin. So if it's random true 0.05, that means I have a 5% chance of returning true. Otherwise, it's false. If it's random true of 0.5, I have a even chance. In other words, half chance of getting heads, half false. Half a chance of getting false. So in other words, heads being true, whatever. So if it's random true 0.9, I have a 90% chance of getting true. Otherwise, 10% chance of returning false. This returns a Boolean. And that dictates the condition of leaving. So this is a nice idea, but there's one fly in the ointment. One fly in the ointment. What's that fly? If I run this now, what won't happen? Very likely. The first person won't get infected. So we need to change that. we need to add one more transition here. And this is one of the reasons for leaving introduction of this. I'm going to have a force infection transition. This is one of several ways to do it. This is going to be based on a message, and the message will be force infection, exclamation point. Notice I capitalize it with a capital F and a capital I with no space between them and an exclamation point at the end. And I'm going to copy that exact message over to here, where I send the initial infection, and I'm going to send that as my initial message. Okay. And finally, I am going to set this other transition, this exposure transition, to be on a particular message exposed. So what did I do? Let me rehearse that. I put in a new transition. I set it to only go, it's a message transition, but it only transitions on a particular message force infection, like that. Secondly, I went back to main, and I had the initial infection event send that exact message to a random agent inside. Thirdly, I went and I set the exposure event to only transition based on the exposed message. So basically, I distinguished between the first person who always is infected and other people who are only infected with the probability as dictated by this. Notice for this transition here, I made it a condition transition. That's why it's no longer in red. Whereas this one, so it's no longer dotted, I should say. This one is a default. If it isn't true, they just stay susceptible. Okay. If they don't get infected, they just remain susceptible. Okay, so let's go check it out. Okay. Here we are. Okay, so now we've made the model quite convincingly similar to the original. But still, there seems to be only one outbreak here. Only one outbreak. Because we still haven't changed that issue that the infection can die out completely out of this population. The stochastics that matter here. The infection can die out, and then it's not present at all, and there's no way it's going to infect some. Okay, just one or two more things here, ladies and gentlemen. So I am going to go, and I am going to place in the population here a statistic. So I go to main, go to the statistics area of population, and I will place a statistic that we called count infective, ABM. This will be a statistic on the population, and it's a count statistic. And what will the condition be here? Remember that each person is in turn called item. So what will the condition be? Item dot in state person dot infected. This is very similar to something we did in our last class, where we had a statistic and it counted the number of people who were afflicted. So ladies and gentlemen, what did I do? I went to population in Maine. I went down to the statistics area. I added a new statistic, called it count infective ABM, made it a count statistic, and the condition is item. So each person in turn in the population is being called item. And we're asking for that person, are they in a certain state? What state is it? Well, it's the infective state within the person class. Okay? And now, for this graph, I want to plot out the number that are infected. So I'm going to call each of these titles susceptible SD, infective SD, infective and recovered SD. And next, I'm going to, oh man, I'm going to go and create a new one that's going to be called, infective ABM. Okay, here we go. Infective ABM. Boom. Okay, infective ABM. And what will the value of this be? It will be this dot population. I'm asking the population to compute the value of its statistic, which we can do by simply calling the name of the statistic. So this dot population dot count infective. Okay, we just call it like it's a method call. Count effective ABM, begin paren, end paren, because it doesn't need any parameters. And now, if we run this model, we will see how the number of infectives in this ABM compares with the number in the SD model. Okay. Now time is just about up here. I'll make one final point, and we will break now. Okay, so I'm going to run this again here. Here we go. What do you think we'll see now? How do you think the number of infectives in the ABM and the SD model will compare? Will it be closely or far apart? Close or not? Okay. SD, the infective is shown as red. For ABM, the infectives are shown as what color? Blue here. So you actually see it does capture an initial growth, and then it goes down, and then it rises again. But it's a little bit off in terms of the numbers. It's a little bit off in terms of the numbers, ladies and gentlemen. Okay. The final thing I'll ask you to do here is to simply go up above where you'll see a short duration infection. And I will ask you to go scroll down and change the stop time there to be also 1,000. We're going to full time, the full time we want to see. And here I will further ask you to change the time infective, ladies. Excuse me, this is short time infection. I should have said short duration immunity, I'll call it. Short duration immunity. That wouldn't have been how I wanted to do it. The mean time to recover here, we will reset to its original value here, which was 10. So the mean time to recover will be 10. And the duration of immunity, ladies and gentlemen, will be also 10 units, okay? Okay, I'd like you to run this. So the mean immunity duration. So we have a very short duration of immunity. Very quickly after getting recovered, they can go back susceptible again. How do you think this will change things? How will it change the burden of infection? How do you think it will qualitatively change things? The infection won't die out. Why was it dying out before? It was running out of susceptibles. Well, it was actually running out of infectives to infect susceptibles. So people stayed recovered for so long before waning immunity that all the infectives died out. So when they became susceptible again, they were never infected because all the infectives were gone. All the infectives had themselves transitioned to a recovered state. So by the time people went back and got susceptible, there was no infectives around. Now, why is it different now? Yeah, people are losing their immunity early, and while there are still infectives around. And here you see this go up to a level. It looks different at first. The infection spreads, but it goes up to a level and stays resident. Why is it staying resident? Because by the time they lose their immunity, there's still infectives around. So it stays present. And you'll notice that here we can compare the number of infectives here in the SD with the number of infectives in the ABM. Interestingly, the number of infectives in the SD doesn't. It's here. It's 375. So I'm guessing it's just overlapped with this gray one. Exactly. And we have a somewhat off number of ABMs. You notice this oscillation. Why oscillations? Why this sort of movement? Stochastics, ladies and gentlemen. Different individuals recovering, getting infected, spreading it. Different people happen to be around when someone loses their immunity. Sometimes there is someone around who's infected. Sometimes there's not. And so you see this variability here. And early on, quite big differences in what's going on. It spreads a lot more slowly. Why does it spread very slowly here at first? It spreads slowly because it spreads locally. It spreads out to neighbors only in this network. So we're going to come back to this. But here's an example, in contrast to last time where the two models were completely aligned. Here's an example where they could be totally different because of extinction of infection and because of the way the infection spreads and because of issues having to do with stochastics, which throw it off some, and the fact that some of the same people I keep on exposing to infection are the same people I exposed earlier and earlier and earlier. So I'm not mixing as widely within the population. We'll come back to this example. Thank you very much for your patience, and I'll post this model right after class here.